Hello, we are Luka, Patrick, Chris, and Juntong of Team Deinonychus. So we all know the process of organizing photos can be a huge pain, and when they aren't organized, it's still a pain to search through huge unsorted folders looking for that one photo you know you took. Our project looks to solve that problem using some of our main features, which are as follows. Category tags. So this component uses machine learning to identify objects in an image, then using these detected objects, it can tag the image with one or more supercategories. Categories include portrait, group photo, urban, pet, nature, sports, and food. Next, we have the name tags feature. The name tags feature identifies people in an image and tags the image with their names. Next, we have the rotation correction feature. Although the rotation correction model doesn't actually help with the organization of photos, it does detect crooked images using machine learning, then straightens them out and returns them to the user. Finally, we have the low light enhancement feature, which, like the rotation correction feature, doesn't actually help with the organization, but it does detect dark images and outputs a better lit version for the convenience of the user.
Okay, so here's how our application works. First, you upload a few photos by either clicking the upload box or dragging in your photos. And then you select which machine learning models you want to process your photos through. For now, we'll just select the photo categorizer, the facial recognition model, and the rotation correction model. After you've selected which models you want to run, simply click Run Features. And now we have to wait while the uploaded photos are being processed. With the number of images I uploaded, this will take around 30 seconds. Okay, now that the machine learning is done, we can view our images by clicking Gallery. And all of our uploaded images will be displayed here. If we click on an image, it will expand it and show all the categories that our machine learning model tagged the photo as. As you can see, our machine learning model is pretty accurate with its categories. If you want to modify any tags, simply expand an image and click Edit Tags in the bottom right corner. And if we expand the image again on the gallery, you can see that the tags have changed. Once you're happy with everything, you can download the photos by clicking Download Photos. If we look at our photos, we can see that the files have become updated with the tags from our application. Also, we can see the rotation corrected photos. Let me also show you how to set up for the facial recognition feature. In the project files of our application, navigate to the temp directory and then its subdirectory named Faces. In Faces, add a new directory with at least 7 unique and clear photos of someone's face, or more depending on how many people you add to this Faces directory. You also need to name this new directory with the name of the person you're adding.
Here's a walkthrough diagram showing the structure of our app. The app is separated into two parts, which are the front end and the back end. In the front end, we have a home page and a gallery page as our main pages where the user can interact with our application. As for the back end, we have a class named Image Library to store images and their tags, and a package named ML Backend to hold our machine learning models. So, after the app is launched and the user clicks the Run Feature button on the homepage, the app will read images from the library and run these machine learning models to find the tags or to enhance images. Then the tags and images will be added back to the library. Additionally, the user can also go to the gallery page to view images and edit their tags.
So as Juntong mentioned, when the user clicks Run, it runs all the machine learning models in order to tag the images. 2 of these models are the pre-trained and custom YOLO v5 models. The reason we chose to do 2 separate YOLO v5 models is that in order to add our new custom classes to the pre-trained model, we'd have to train the combined model on all images from the 80 classes the pre-trained model, as well as adding the custom objects we want. We felt this would take away from training and experimenting time we could have with our custom model, and since our application runs pretty quickly anyway, it doesn't really inconvenience the user in the end. So the pre-trained model was not implemented by us, but is directly available for download from the YOLO v5 repository. It has 80 classes, of which you can see some here. We have car, bird, cat, and dog, and each of these classes links to a super category tag. So as you can see, car links to urban, nature, bird links to nature, and cat and dog link to pet. Next, we have the custom model. So the custom model was trained by us using Google's Open Image dataset, which has a large variety of different objects available for training, as well as providing bounding boxes for the model to learn from. We trained the model on skyscrapers, trees, flowers, and plates. And here I have a notebook of some examples of how the model performed. So as you can see, it has fairly high accuracy. It's 0.43, 0.58, and it's generally capturing all the flowers. So next we have an example of some plates. Again, it has quite high accuracy, 0.84, 0.85, and it has a nice bounding box. Next we have trees. Again, nice accuracy of 0.62, and the bounding box is perfectly capturing the tree. And finally, we have skyscrapers. Here you can't really see the accuracy, but we can tell the bounding boxes are finding pretty much all the skyscrapers. Finally, some limitations with these models are if the image does not contain any detected object, for example this beach picture, the model cannot predict anything because it does not have an object class to link to a tag super category. So although this image would ideally be classified as nature, it actually has no tags, as you can see, because the model could not find any objects in this image.
For the rotation correction feature, a custom trained model first detects if an image is crooked. If the image is more than slightly crooked, the model will straighten it. The dataset was formed by taking sample images and rotating them and cropping them so that there are no black bars, using how much it was rotated by as the label. The L1 loss function was used to train the ResNet 18 model to predict values as close to the image labels as possible. With this training method, our model was able to predict how much an image was rotated to within a couple degrees, achieving greater accuracy when there are well-defined vertical and horizontal lines. The next step in our application development would be to enable users to manually adjust image rotation. The low light enhancement feature is implemented by calculating the average pixel in an image, which is used to determine whether an image is dark enough to benefit from running through a custom-trained Inception ResNet v2 model. The dataset was formed by taking sample images, adding grain, which is often found in low-light images, and decreasing their brightness. For images where we artificially added grain and decreased brightness, the model was able to achieve remarkable results. Real-world performance, however, was more hit or miss. If an image was too dark, the model would not be able to detect any color in the image to enhance. If there are bright spots in the image, the model would produce neon spots. This feature is still in beta because these neon spots ruin an image. Moving forwards, we might have to rethink how to implement this feature in order to avoid the issue. The name tags feature is implemented through two machine learning models, one for face detection and the other for face recognition. The detection model is used to crop faces in the image to use as the input to a recognition model. Since it serves as the input to another model, it has to be super accurate. This is why we decided to use a pre-trained FaceNet PyTorch MTCNN for the task. The recognition model then predicts which person the face belongs to, using a SVM from scikit-learn for its quick training time. Lastly, the names of people are added to the image's tags. With this model, we can expect to achieve 60 to 80% accuracy when distinguishing between 5 people, provided that there are at least 7 images per person in the training dataset. To distinguish between 10 people, 14 images per person would be required. Here you can see that the predicted class often matches a face's true class. We used linear discriminant analysis as it was consistently one of the top performing classifiers. Ideally, users would be able to classify faces from their uploaded images within the application. However, with their limited experience in web development, we were not able to fully implement this feature for the project deadline. In its current state, the face recognition model would train on images labeled and placed in a certain directory. More details regarding this manual setup process can be found on the application homepage.
Let's discuss some key takeaways that we learned over the course of this project. So first of all, because of online classes, all collaboration was done electronically, making it especially important that our communication was strong and effective. At the beginning, we worked mostly separately on different components of our project, but then around the middle of it, when we started connecting those components together, our work began to overlap, so we had to make sure our code was clear and easy to read, since all four of us could be working on it at once. On the web development side of things, we were introduced to a bunch of programming languages such as HTML, JavaScript, and CSS, as well as further enhancing our experience with Python. Our application was developed using Flask, so we had to learn how to use that as well. And finally, for the machine learning development aspect of this project, we built off already existing models by training them on our own custom datasets to meet the needs of our application. The forming of datasets made up a large core of our work with machine learning. As well, we had to learn to integrate the machine learning models to the desktop application we developed. Thanks for letting us walk you through our application and its development process. We're Team Deinonychus, and we're pretty proud of what we made, as well as the many concepts we learned along the way.